we would like to challenge problem 4, shooting rubber band.
Problem 4.
We accept.
Accept the problem 4. Shooting rubber band. Reporter, you have 5 minutes to prepare your report. Each team, please write down the name of your presenter on the board. hold your wrist, take the floor.
Alright, honorable judges and fellow competitors, this is a reporter from Team Excalibur, and today I'm reporting for round number 4 and shooting rubber band. So, this is a problem statement. So, when a rubber band may fly a longer distance if it's non-uniformly stretched when shot and give it a spin, so we need to optimize the distance that a rubber band with spin can reach. So, so this is the observation. So, when it's upper view, so you can see that in the upper view, the rubber band might fly forward with non-uniformly, like this. And when you do it unevenly stretched, so it may fly forward like more circularly. So so now we are talking about the shooting projection. So first of all, we shoot the rubber band parallel to the ground. And so we can use this formula to calculate the final distance. And we use a comparison, and we consider it as two springs with parallel connection. So when we stretch it like this, it looks like two springs working. And this is a Hooke's. So because we consider it as a two spring, so we can use Hooke's law to find out the relation between the force and the elongation of a rubber band. And here are the data. So the area between two orange lines is where the Hooke's law can be applied. And so we use fit to get the elastic constant, and you can see that from the forward, it may not look like a linear line because it's a rubber band and it's still different from a spring. So now we can describe the phenomenon. So this is when it without a spin. So when it's evenly stretched, it creates forces that makes the rubber band may fly forward. So it's like shooting like this, so it may fly forward. And so when it's without a spin, so we can know that force will equal to the kinetic energy plus the internal kinetic energy plus the energy loss. And so we can get the alpha as the energy conversion efficiency, which is basically the kinetic energy over the force that was created. And so this is a shooting distance without a spin. We can use this formula to get. And so when it's unevenly stretched, it creates different forces that eventually leads to a spin. Yeah. So now we can try to measure the elastic constant. So so the elastic constant would be proportional to area over L. So in the experiment, the change of area can be ignored because the area is basically the area of the spring, and because the area of the rubber band is too small, so we can basically ignore it, and we can use K is proportional to 1 over L to do the proof. And we add the force, and we add the mass to the rubber band. So we can get this data. So when we stretch it differently, and the elongation will differ, and it may fit to the K. It's proportional to 1 over L. So now the elastic constant of the spring is proportional to A over L. So therefore, the left side of the spring and the right side of the spring will have different elastic constant. So the one we use L x to describe the left side of the spring, and we use 2 times L0 minus x to describe the right side of the spring. And now it's the energy transfer. So so you can see that we can write down the left side of the left side of the springs kinetic elastic constant to this, and the right side of the springs elastic constant to this, and we can get the beta. So why we're ignoring 1 over 2 times I omega squared is that because we only need to know the kinetic energy of the whole experiment. So we choose to ignore it, and it doesn't contribute to the final distance. So now we can get the shooting distance with spin. And it may look like this. So now we're going to talk about the setup. So we use this launcher that imitates how we grab grab the rubber band, and we use tripod to film the experiment, and we use back cardboard to make us can see the experiment more clearly. And now we need to determine the relation between the elongation of the rubber band, which is L minus L0, and alpha, which is the energy conversion rate. And so the mass of the rubber band will be 0.32 gram, and the elastic constant will be equal to 0.1724, which is mentioned before. And we use a high-speed camera. Also. So this is the experiment video, and we use this tracker and Excel to analyze the data. So the alpha may look like this. So in this area we can see the trend of the line, and so in this point, so we consider it as the critical point when it can fly forward more. So when the rubber band is shut like this, it may not fly forward that much. But if it's slightly more stretched, it may fly forward. So it may be the critical point that we are thinking of. So, and the experiment too, we did the final distance. We need to determine the relation between the final distance and the strict length, and which is without the rotation. And we also use this tracker and Excel to model it. And so this is the graph right here. And so we use this, we fit it, we left it. So this is a theory line, and we compare it to the data of the experiment, and the alpha here we put in would be 0.798, which is the average of the multiple alpha that I mentioned above. And so this is a third experiment. So we need to determine the relation between x and beta. The x is what we previously mentioned, which is the left side of the length of the left side. And we also use this tracker and Excel to analyze it. So the first experiment, so the x will equal to 0.45, which is no rotation. So it will look like this when we pull it. And so the x will equal to 4.86, and you can see that we put the hand slightly more right to the rubber band. And when x is 3.24, the beta, so we can see that we put the hand more right to the rubber band. So to see more clearly, so this is basically where we put our hand, and so the x would, and so the beta to x graph would be looking like this. And so the fourth experiment, so we need to determine the relation between the final distance and x. So this is experimental data. And so we compare it to the theory, and the beta here would be roughly equals to 0.759, and which is the average of multiple beta mentioned above. And so now we get into the conclusion. So this is the problem statement. So a rubber band may fly forward by a longer distance if it's non-uniformly stretched when shot and given its spin. So we need to optimize the distance that a rubber band with spin can reach. So the main focus that we did in this experiment is that the distance that the rubber band can reach with rotation and the energy conversion efficiency of the rubber band in different conditions. So now we'll talk about why. the rubber band may fly longer. So if the rubber band was stretched unevenly, the elastic content of two sides of the rubber band will change. But if the rubber band has a spin, some potential elastic energy will be transformed into the rotational energy, which should make the rubber band fly shorter, right? If you explain like that. But, so in our actual case, the initial elastic potential energy will be bigger if the rubber band had the spin. So therefore, although some of the energy will be transformed into the rotation energy, the kinetic energy will still be bigger, because that initial elastic potential energy will defeat the actual energy loss. So now the conclusion part. So we make sure the Hughes law can be applied, and we also measure the elastic constant which change with the length. And we also define alpha and beta to explain the energy transfer. So it will look like this. And so that we optimize the distance that a rubber band with spin can reach. So we can get that when more spin is given, the R will increase. But when it's in the actual case, you cannot stretch it that much because the actual rubber band may break. So we cannot test its final limit. So that is the point for presentation. Thank you.
Okay, question of the opponent will report.
According to the problem statement, it says that it would need to optimize the distance. So did you optimize the distance?
So we did optimize
treating
this.
your rubber band.
We cannot optimize how spin can reach, but when you stretch the rubber band, when you stretch more, it will fly more until the rubber band may like fatigue or something, so that it cannot be used anymore.
So did you know the ratio between the more stretch one and
Yeah. So
less
this is
stretch
a ratio here. So we basically grab this, and when we hold it like this, and this. So did that answer your question?
one? Okay. On page 34.
So on page 3.
Can I ask why is that linear?
So in this formula, we can get the so the R would be a linear line.
So, okay, that's fine. And I want to ask that how do you shoot the rubber band while the experiment?
So we in the setup part, so we actually use this this thing, and also I talk about it in the setup. So this is a function. So we basically we use it, and we grab the rubber band from here, and we put it right here, and so when it's released, it may fly forward.
Okay. So you mentioned that the K in your experiment is constant.
Yes.
But you have mentioned that the K is proportional to the area of it.
Oh, time's up. Opponent, you have 3 minutes to prepare your report. opponent, please take the floor.
Honorable judges and worthy opponents, this is Team Me Too opposing the problem for string rubber band. And here's the problem statement. And the problem states that we need to optimize the distance that a rubber band with spin can reach. And the reporter focuses on the phenomena and the problem focuses on the explanation of phenomena and optimize your distance. And so the summary of the report, in the phenomena, they state that the evenly stretched cause force and the force caused the rubber band to fly forward. And unevenly stretched caused the spin and caused the force and which can fly even more further with the evenly stretched one. And to the theory, they explain that they use two strings to modify the model, and they use Hooke's law, elastic constant analysis, and they use energy transform to explain why unevenly stretched rubber band will fly further. And for the experiment, they use long strips and shot it to a black cardboard and shooting projector. They use relation between the elongation and energy conservation rate, and the relation between final distance and stretch length, and the relation between the length of the left side of the rubber band and the rotation. And they experiment the relation between the final distance and the ratio of the unevenly stretched line. About the pros and cons of the report. Pros are they have clear visual to show the motion of the rubber band and detailed explanation on the formula they derive. On the cons, they only discuss one way to make the rubber band stretches unevenly, and they lack concrete experimental data, and they didn't quantify the maximum distance that the rubber band can reach. And the furthermore discussion. While theory, we're going to discuss the theoretical results that compared to the experimental one, and the K value of the rubber band, and the energy transformation while shooting the rubber band, and the kinetic energy distribution of the X and Y axis, and the ratio value of the rubber band while the theory derived. In the phenomenon, we're gonna discuss about the energy stability while spinning the rubber band, and we're gonna discuss the launching angle and how temperature will affect the distance of the rubber band. And I would like to invite the board to the stage. I don't want to ask that the K value of your theory, and you have said that the K are proportional to the area and the length of the rubber band. But you also said that it is a constant while experimenting. But I think that if there's force acting on the rubber band, the area of the rubber band may be smaller, and the length of the rubber band will be larger, and hence the K won't be a constant.
So the K is so the K actually means that here, sorry. So let me show you. So the K actually means that when we take this, and the K is actually the value of the line to when it's crossed like this. So this is a K.
Yeah.
So when we stretch the length in this area, which is like roughly 6 to 12 point something cm, so the K will be the constant.
So you mean the K is the slope of the
Yeah.
And What do you think the energy transformation about the unevenly stretched rubber band to the velocity of x-axis, or what do you think?
So what do you mean like velocity of the x-axis?
Because you mentioned that there's energy transformation, and I want to know how the the energy of spinning that leads to the energy of velocity, because there must be more velocity while spinning that leads to the further distance of the rubber band.
Right. So in this PPT, I explained that so the initial elastic potential energy will be bigger, so that it can defeat the energy loss. So it may have the higher velocity and eventually a longer distance. Yeah.
So do you think that the spinning decrease the air resistance while flying through air,
So I think
or you think it's the energy?
so the spinning is so the air resistance doesn't do that much in this experiment. So it's mainly the spin that so it's mainly the energy that is given so that it can make it fly longer.
Okay. And I want to ask if you change the launching angle, do you think that the energy transformation of the spinning and the kinetic energy will change, or no?
So yeah, that's a great question. But so in the actual problem statement, it states that optimize the distance when a rubber band with spin can reach. So I think if you change the launching angle, it's like out of the problem statement area.
But I think if I'll optimize the launching angle while optimizing the distance of
so I think the problem statement states that we need to optimize the distance with spin. So so I think the change of the launching angle would be actually out of the problem statement. So we didn't do the experiment.
And I want to ask, do you have the exact value of the ratio between the more stretched one and less stretched one in your theory?
Ratio?
Yeah, the ratio. The problem statement states that it's unevenly stretched, and
Yeah.
I believe that the ratio of the rubber band can leads to the theory that there must be a greater distance.
So we actually draw like the 8 points that can divide the circle. So we mainly these 3 points is that we can have the ratio to do the experiment. But other 3 points that we did the experiment, but we didn't calculate the exact ratio. And it's actually that so we didn't calculate the actual ratio. So I think maybe it can be more clearer to explain, but we didn't calculate.
Okay. So another question is that, do you think that the spinning of the rubber band can affect the energy stability of the rubber band while flying through air?
Yeah, that's a great question. So so when you shoot the rubber band with spin, so in the air, so it may actually affect the stability of it. But when it's given the moment, when it's shooting out in the air, so it may cause the extra moment of inertia, so that may cause the effect of the stability. But I think that doesn't really contribute to the final distance. So yeah.
So do you mean that the inertia of spinning, the energy of spinning of inertia that leads to the energy of the velocity that leads to the distance of further distance of the spinning? Am I correct? I mean that because there's a spinning, there's energy source in the spinning inertia. So there's, you mentioned that the energy transformation is that their spinning cause the further distance.
Yeah.
So it's the spinning
So
that
I
leads to the energy transformation.
yeah.
Okay.
And the moment of inertia may affect, but it doesn't contribute a lot to the final distance.
And another question I want to ask is that the temperatures. Do you think the temperature acts on a rubber band can affect its distance? That maybe I think it affects the K value of it.
So we actually did consider it in the experiment. So after every shoot we did, after every set of experiment we did, we let it set, and so it can get back to the normal temperature. So it can affect this.
Okay. So as you mentioned that in this graph that I assume that this is the ratio of the stretch length.
Yeah.
And in this graph,
This is the x. Yeah.
yeah. So this is
No, this is beta. So beta is the energy conversion efficiency
So-
of when it's had the spin.
so do you think the ratio, if the ratio gains more values, it will be much further distance of the rubber band, or it will have a maximum value of the ratio.
So I think when the x is smaller, it can contribute more to the final distance. But due to the real world conditions, so the rubber band is like this long, so we can only do that much.
You
So
mean the elasticity
yeah.
of the rubber band.
Yeah.
So
so it will change with every rubber band.
So I mean that besides the elasticity fatigue of the rubber band, if the ratio is much more bigger, and this will be
More
much
smaller.
bigger.
More smaller. The ratio. So the ratio, I mean that the stretch thing. Yeah.
Yeah, so
Yeah.
it's less unevenly stretched the more distance.
No.
Or
So yeah, more uneven stretch.
more unevenly
Yeah.
evenly stretched the more distance.
Yeah.
So we think that under the elasticity fatigue of the rubber band value, it will have the more distance flying while the ratio is much bigger.
Do you mean that you don't consider when you don't consider the elastic fatigue?
Yeah.
Yeah.
And one and that's all my question.
Yeah, then please summarize the discussion.
In this discussion, we mentioned that the K value of the rubber band, and we also specified on the energy transformation while spinning through the velocity one, and the kinetic energy distribution, and the ratio value of the rubber band. And the report states that if we don't consider the elasticity fatigue, the more unevenly stretched the rubber band is, the more distance you'll get in the experiment. And we also discussed the temperature impact on the shooting distance, but the report considered it as a negligible value in the experiment.
Question the reviewer to report an opponent.
Okay, so I'm the reviewer of problem number 4. So can the reporter first turn to page 11? How do you define these two orange lines?
So these two, which is basically, so when we can observe that it is stable, that it's a linear line.
So why can't I define the left line and then move it to 4 when the elongation is 4? I think it's pretty like regular too.
So yes, you may do that, but in the experiment we choose not to do that much, do to that part of that. because the
So if-
because
if-
the
if
oh,
we-
also so the actually the original length of the rubber band is already 6.05
Okay.
centimeters.
Okay, so can we move to page 18? Yeah, 18. Okay, so I know that when we stretch rubber bands, the A over there means the area of the cross section area of the rubber band.
The area of a rubber like this, just only like the area of this.
Okay, so don't you think that when you stretch it, the area will be different?
But it's too small that we can basically ignore it because the rubber band is too thin.
Oh, okay,
in
okay.
the area.
So, and then I want to ask the opponents, you mentioned about temperature, and I think they didn't mention that in their theory. So is it your experiment result, or do you think it's necessary to discuss that?
I think that the temperature of this experiment may affect on the molecules in the rubber band.
Okay.
So,
Do you think you should consider that?
I state that I already considered that, and we after every
Okay.
experiment we did set for like 3 minutes or
Okay.
more.
So can we go to page 34? Yes, so can you explain, like, your theory is a red line, right?
Yeah.
And then, so why is your, like, results not linear, and then you still draw a linear line?
So this is a theoretical line, which in theory it may be linear. It
Okay.
should be linear.
So how do you explain this? Is it human error, or?
So I think because alpha, I think alpha will be like the experimental result. So I think
So is it the?
I think it's the energy
Formula.
loss. I think it's the
So when I can see in your observation video the.
Time's up.
Okay.
You have just to compare. Okay, reviewer, please take the floor.
Okay, so I'm the reviewer for problem number 4. And this is the summary for their report. So they applied the Hooke's law as their theory, and then they also had discussion on the elastic constant, and they also discussed the energy conversion rate, and then they do experiments when they stretch the rubber band unevenly. Okay, so this is the reporters. Some pros for the reporter is that he has comparison between the videos, and he defined alpha and beta to discuss, which is pretty new to us. And then for some of the cons, I feel like they have too much complicated settings, and the definition is not not really clear. They could have like presented or shown it more clearly, and then they didn't mention what the problem asked, like the maximum distance, which is what the opponent has mentioned. And then this is what this is about the opponent. He pointed out crucial questions of the problem statement, and then he also had a great summary of the report. Okay, so this is the question from the opponent, so how the energy transfers, and then the reporter answers. The initial energy will be bigger, and bigger enough to cover the energy loss on spinning. And then the another question that the opponent asked was about the air resistance, but the reporter said that this is not one of the factors that they consider. Okay. So the opponent also asked about changing the launching angles, and then he asked like what will happen, what will be the difference of the phenomenon, and then the reporter says that this is out of what the problem statement wants to investigate. And the opponent also asked that do you have the ratio of the unevenly stretched rubber bands, and then the reporter had some of the ratios, but then he also mentioned that he didn't calculate other ratios. The opponent also asked that do you think the spinning can stabilize the energy of the rubber band, and then the reporter answered there will be extra moment of inertia in it. The opponent asked do you think temperature affects, and then the reporter says he did consider, but it doesn't impact a lot. So this is the question from me, the reviewer. I asked about the Hooke's law boundary, about the two orange lines, and then the reporter said it's linear and stable, and then I didn't ask the opponent. And then this is another question. I asked about the cross-section area, and then the reporter said it is too small, and then because of the rubber band is pretty thin, so it could be ignored. And I also didn't ask the opponent about this question, and I think this would probably change. So I think it should be considered. So another question for the opponent is I asked about the temperature consideration, and then the reporter told me that he considered it in his theory, and then the opponent says that he thinks that it would make a difference, and I agree with the reporter. Okay, and this is the question about theory and experimental result, and then.
Time's up.
Okay, thank you.
Concluding remarks from the report.
Right. So this is a concluding remark from the reporter. So the theory part, I used Hooke's law and two-spring model to explain the theory and the elongation, to know the elastic constant and the energy conversion efficiency, and also the projectile motion to explain the theory. And the experiment, we use this force sensor to prove Hooke's law can be applied, and differentiate the unevenly stretched length, and we also differentiate the distance with spin and without spin, and we use tracker and Excel to analyze the data, and we also use high frame speed camera to take videos, and we use a controller to shoot the rubber band. And so this is the conclusion. We optimize this. When we optimize the shooting distance, so when the elongation of the unevenly stretched is longer, there is more initial potential energy, and also there is a critical value of the rubber band that makes the final distance increase. So also, when more spin is given, the final distance will increase. And compared to the theory line, there are still some energy losses, and it may causes the error. So this is the theory part. So we discussed that we need to optimize the distance by using the unevenly stretched length, and how the theoretical value align with the experiment result, and that the effect of spin would affect the stability, and how the moment of inertia affects the final distance, and we also discuss how the temperature affects the rubber band, and we actually did that in the experiment. We let it set and let it return to the return to the temperature that it used to be. So the temperature wouldn't affect in our experiment. So we actually did that, and so so there are some experiments that we discussed. Yeah, thank you.
Now is a question from the jury. Any questions? Yes.
For the reporter, if I remember correctly, the figure shows that the data points look like linear by your theory. This figure shows that the data points look like linear.
Yeah.
But your theory is not. That's not linear. It's not linear.
It's not which one?
Theoretical curve.
On theoretical curve. So that is when we given it a spin. So that wouldn't be linear because the formula itself it wouldn't be linear.
So, do you think that your theory is too more complex? Do you need to simplify it?
But so we actually compare it when we there is actually a larger graph that we consider. So the graph will be looking like this, and our point is like basically situated here. So I think our theory point our theory point is actually on the track, and we can. So although we didn't consider the shorter x, and so the graph. So we didn't consider where the point would be here, but we did get the data here. So I think that it fits the theory.
Okay, so do you have a comment on this?
You mean that the theory and experimental result doesn't quite match? I think one possibility might be that there is still energy loss that he didn't consider about. Like I saw in the observation video, it's not only the potential kinetic energy and then this rotating energy. There is also like the wave, it's also moving vertically. So I think maybe they have to also consider that, and their results might match their theory more.
I think because the K value isn't the constant, because if there's force act on a rubber band, there will be an different from the constant K, and I think that the error from the difference between the theoretical model and their data points might be the K value.
Are you sure everything's again the even fixed rubber band will fly longer?
So this device is showing up power. So can you
I need to see the evidence again. How the unevenly stretched rubber band fly longer distance?
So basically, when we grab the energy, when we grab
I'm asking more
evidence, right? So the data.
Yes.
Okay. It's
Now let's switch. Then you said the unevenly stretched rubber band will have a larger energy to cover the loss of energy through the rotation of the rubber band. So what is the theory? I still don't quite follow.
So do you mean that there should be a formula for it?
I assume you get a formula.
So we didn't have a formula to calculate the motion while it's in the air, but because
No. You said the energy unevenly stretched rubber band will have larger energy compared to the evenly stretched rubber band. So my question is, where does that come from?
So it's the assumption that we made because it's like the more feasible explanation to this phenomenon.
So you pick it without verifying?
We had the data to prove it, but we didn't have the formula because
What is the data you have? No, energy. You talk about energy, right? You said it has larger energy to begin with, so it flies longer distance. So the evidence is not the distance, it's the energy. So how do you estimate there's a larger energy on the unevenly stretched rubber band?
So basically, so what we explained is that there will be the initial potential energy, and so combined it with we just combined it with the data. So
How?
so we can consider we found out that when it's evenly stretched, the distance will be shorter. So the energy, I think the energy part, yeah, that's it.
Any more questions? Okay, now jurors, please prepare your score. Okay, please show your score to the reporter. 66764. Now the score for opponent. 55655. Score for the reviewer. 55655. Okay, thank you for everybody's participation. I think this section is closed.